Hello, it's Mr. Powers. I'm teaching math. We're doing algebra. We're doing recursively defined sequences. And what better sequence to look at than the Fibonacci sequence? Now, how do you spell Fibonacci? How do you spell that? Here. This is how you spell it. There it is. All right. And this is a super fun one. It's got a special name, special definition. It's got all sorts of really fun properties. So if you are bored and you want to look it up, you can totally look this stuff up. But it starts off like this. And there's a couple ways we can start. I'm going to start at 1. Oops. Sorry. Okay. I'm going to start at 1. And then we're going to say another 1. Then my next number is going to be a 2. Then my next number is going to be a 3. Then my next number is going to be a 5. Then my next number is going to be 8. What will the next number be? Okay, the next one is going to be 13. Do you know what the next one's going to be? All right. The next one is 21. Okay. And so on. Now, how did we get 21? Many of you guys figured it out by now. 13 plus 8 is 21. 13 was 8 plus 5. That's 13. 3 plus 5 is 8. Now, if you're looking for, like, are we adding the same thing every time? You were like, no. I add 1 here. Then I added 2. All right. Then I add, so maybe I'm adding different ones here. Then I add, what? Add 5? Oh, this was add 3. So you might see it. Oh, there's the 5, there's the 3, there's the 1. You're like, oh, okay, wait, I'm adding the one before it. Maybe you could find it that way, right? But they're definitely not multiples of the same number. They're not powers of a number, right? So you got to look for something a little different. So in this one, you take, to get the next term, you take the 2 terms that came before it and add them together. And that's the Fibonacci sequence. And we get the golden ratio out of this. As you continue moving on, you take any 2 of these terms, like right now, my last 2 are 21 and 13. You take those terms, the further along this sequence you go, the closer these terms, when you take their ratio like this, approach this thing called the golden ratio, this magic number. I think it's like 1.645. I'd have to look it up. Not really important right now, but it appears in nature all over the place. They say beautiful people have ratios in their faces of the golden ratio. It's all over the place. It's really neat. And these numbers also appear all over the place. You get, how many petals do you see on flowers usually? 1, 2, 3, 5, 8, 13, 21. Those are the numbers of flowers you see. Spirals on like a pineapple or pine cones. How many spirals do you see? Lots of times it's going to be these numbers. It's really neat. So it's kind of a fun sequence. But now, if you're trying to explicitly define this sequence, like we did with the other ones, like, like here, where we had 3n plus 8, so we could get certain terms, or we had 2, 4, 8, 16, and we figured, well, that's 2 to the n. These are powers of 2. And then if I want the 5th term, I just plug in 5. If I want the 21st term, I plug in 21. If you want to get an explicit term for a Fibonacci sequence, well, that's going to be a lot trickier. Very difficult. Using recursive algorithms and programming can make it very easy. It's like a couple lines of code. But if you're trying to do this in an explicit way, like just straight up formula, plug the number in, it is difficult. I don't know how to do it. I don't know if there's a way to do it. So what is the formula in this case? If we call this one F1, our first term, and I'm using capital F because this is, whenever you see capital F, we're talking about the Fibonacci sequence. This would be my second term. Here's my third term, F3, and so on. Well, how do we get F4? Well, F4 was F3 plus F2, right? Let's look at this one. Here's my fifth term. My fifth term was the fourth term, F4 plus F3, right? So I'll give you an example here, and let's do the fifth term. Let's try to find the fifth term, and I'll find it using the definition. And you'll see this is actually a little bit of work, but it's neat how it works, and it does work. But the problem is we have to define explicitly one or two or three of the terms somewhere in the sequence. And usually we'll pick the starting terms. So I want to say, hey, F1, I'm going to just say is 1. And I'm going to say F2 is 2. And then I'm going to say every other term, F sub n, is going to be the two terms that came before it. Or am I going to, there's a couple ways I could define it. So like I said, I'm going to do so I'm going to define it just like that. So it's going to be F sub n plus 1, or n minus 1, plus F sub n minus 2. Right? And I already have that. What's 5? 5 minus 1 is 4. There's my n minus 1. 5 minus 2 is 3. There's my n minus 2. All right? So we can see, yes, this is exactly the definition for this function. And that we call this kind of a definition a recursive definition of a sequence, where you have your defined terms and then you have the trick to getting your other terms. Then you have kind of like your rule here. Like we already figured out, to get any of these, I add the two that came before it. So to get my fifth one, add 4 and 3. Add those two that came before it. And this is how we represent that. F sub n minus 1 is the term that came before the term I'm finding. F sub n minus 2 is 2 terms before the term I'm trying to find. And so on and so forth. And so there we go. We got it. Now, let's work out F sub 5 over here. And I'll show you. This is neat the way it works. It's F sub 4 plus F sub 3. Great. But I don't know F sub 4 and F sub 3, do I? So what do I got to do? I got to keep going. Well, what's F sub 4? F sub 4 is going to be F sub 3 plus F sub 2. And then I still have my F sub 3. But that F sub 3 is really going to be F sub 2 plus F sub 1. Okay, now F sub 2 and F sub 1, I know. Those were defined already, right? So I can stop with those. I can leave those alone. But F sub 3, I need to rewrite. So here, I'm going to do that now. So let's rewrite. Oops, that's a terrible highlight. This one? Yeah, guess. F sub 3. Let's rewrite F sub 3 f sub 3 is going to be rewritten as f sub 2 plus f sub 1. And then I got plus f sub 2 plus f sub 2 plus f sub 1. Oops, I wrote these down wrong. What's wrong with me? F sub 1 is 1, f sub 2 is also 1. So here, I'm going to fix that right now. There we go. And now we can plug these in. Well, each of these is a 1, right? So let's see if I did this right. I'm supposed to get 5. So it's 1 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5. Yep, I got 5. It works. It's super weird, but it works. It's really neat. And so that's an example of a Fibonacci sequence. That puts this video at 10 minutes. So let's go ahead and we'll call it quits right now. But this is a recursively defined sequence. So that's what this is called. We'll use a recursive definition. This is a recursive definition where we have to define a couple terms, and then every other term, its definition is based on terms that came before it, or some formula, some expression that includes previous terms. Okay, that's a recursive definition. All right. So in our next example, next video, I'll do one example where it's just recursively defined, and we're just going to find a few terms. So until next time, enjoy doing math.